Hi everyone, this is Carlos Bernardos, and this is a recording of the session that was supposed to take place today, April the 4th, but due to different, I would say, misunderstandings from you guys and from us, couldn't take place. So instead of having the regular class, what I'm gonna do is to do a quick lecture, recorded lecture, although it will not be a regular lecture, it will be more like going through the key points that I think you should consider when reading the reference book, which is the Kudos book, and when checking also the reference slides, which actually I'm going to be using for this kind of recap. So those are the points that you think I think you should cover, and I'm doing this instead of recovering the lecture because these days you are very busy in terms of assignment and workload, and it will be hard to find a slot that works for all of us and that doesn't involve or doesn't have an impact on the rest of the course, especially because you are one of the small groups that are involved, so it's not easy to decouple that from the big group. So anyway, let's go into that. I will try to make it short but still sufficiently long so you can understand the key concepts. So I will try to go in sufficient detail, although in many places giving like food for thought for you guys to take a look later. So as you can see, these are the regular slides that we leave you in Aula Global. So I'm gonna go through them. So we are in the last part of the course, the transport layer part, and we are in the basically covering TCP, one of the main transport protocols that are used in the internet today. And we're gonna go, what is a TCP connection, or how TCP works in terms of what a TCP connection provides to the application layer and how TCP uses the network layer. Then we'll go a bit into understanding part of that is what is a TCP segment and what are the sequence and acknowledgement numbers. We will see what is that in a minute. And then a bit of how using this TCP provides a reliable data transfer. So TCP overview, what a TCP connection is, or what TCP provides to the upper layers, to the application in this case. Well, there are some RFCs, standards RFC, requests for comments, mentioned in the slide that you could go if you want to go into more detail. Let me tell you that there are many, many more TCP-related RFCs. There are plenty of them, and many extensions, modifications, optimizations, for different scenarios that have been done in the past, and different OSs implement TCP in slightly different versions, trying to improve or optimize some parts. This is something that we're not going to cover in the course in detail, but it's good that you understand that those things exist, because probably there are many different implementations that are compatible among them. Of course, that's the key point of standardizing protocols to ensure interoperability. But it's also true that not all of them do exactly the same things, and there are slight variations. And even as the lectures of the course, we may explain some concepts in different ways because we take as baseline a different variation of TCP. So the important thing is that you get the main concept or the main concepts behind TCP. So TCP is a point-to-point protocol. That means that there is always a one sender and one receiver involved. So there cannot be like one sender and multiple receivers like in UDP. UDP, you can do multicast. With TCP, we cannot do that, especially because there will be the concept of connection established between these two endpoints. So that's an important thing. And because of this connection-oriented, because it's a connection-oriented protocol, TCP can provide some additional features over what the network layer IP or IPv6, IP4, IPv6 provides. What are those additional features? Well, first, it's a reliable protocol in the sense that it will get from the application order data stream, byte stream, so a set of bytes in order, and it will deliver that stream of bytes to the receiver in the same order and with no packet loss or with no byte lost. So it's important to understand that TCP doesn't understand boundaries. So it's expecting a stream of data, and is providing or sending that stream of data to the other end. Of course, applications using TCP may send messages, but those messages will be basically part of this stream, and there may be pauses or parts in which there are no data being exchanged between messages that are covered there, but what TCP uses is the concept of byte stream. So a set of bytes that are one after the other that are received and sent to the other end. And the consumer is basically reading from a buffer and getting those bytes from that buffer and providing that to the application. So that's the concept of being pipeline. So TCP will also adapt how the data is sent by using a couple of things, mainly that is the TCP congestion and flow control. And we will see that later in the course, how this is used to ensure that, for example, TCP tries to maximize the capacity of the links of the path between the sender and receiver while not generating a congestion and while not overloading or going beyond what the receiver can process, because the receiver has also some capabilities and the application is reading from this buffer. And if a sender is sending too fast, that may make the receiver not being able to process all the data in time. So we need to have this buffer, send and receive buffer. So we can see in the figure that we have application writing data in a buffer on the sender side, and the TCP connection or TCP layer will get those bytes from the TCP send buffer and will be in charge of delivering those bytes in the same order and with no losses and no duplication to the other end. And in the other end, in the receiving side, there will be a receive buffer where those bytes will be written, and the application will be reading those bytes from that end. You can see that there is this socket door, so it's the socket, basically the interface between the application and the TCP connection, that is basically the interface to the other end. Remember that TCP is the first layer of the TCP/IP protocol stack that is really, really end-to-end. So process to process, application to application. We have the browser in your mobile and the web server on the other end. So it's a process in your mobile among the many processes that you may have that is consuming what the process on the server side is sending. So this is really end-to-end. As compared to IP, which is not end-to-end yet, is host to host, but not end-to-end from the point of view of the connection endpoints. TCP provides full duplex data capability, so we can send data in a bidirectional data flow on the same connection at the same time. And there is a concept of maximum segment size that we will continue addressing during the course. That is the size of the data unit that for a TCP connection, the maximum size that can be used. So we will see that TCP sends segments, which is the name of the protocol data units at the TCP level, and those units has a maximum size, which is the MSS. Okay, and this is computed trying to minimize that there is fragmentation at the IP layer. So we try to maximize sending as much as we can without fragmenting at the IP layer. So we try to avoid. So the idea is that, of course, we have a stream of bytes that may be continuous. We can think of a file that is sent, for example, using TCP. That is a large file. We have to send that file in chunks of data, and those chunks of data should be encapsulated in segments of TCP, and those segments should be the size that minimizes the chances that the IP datagrams transporting those segments are fragmented on the path or on the way to the destination of those TCP segments. It's a connection-oriented protocol. That means that we have a state on both ends, and we have to do a handshake or basically agree on several parts and establish this state before we can actually send and receive data. And as I mentioned before, it's flow control. So we try, the sender will try to not overwhelm the receiver, and the network will try to adapt to the capabilities of the network and the receiver. And as we will see when we see congestion control, TCP tries to be fair with the rest of the connections that are sharing links. Okay, so there is no one connection that is getting much more data that it deserves to get. Well, how this is actually computed, we will see that when we see congestion control. We will not go into a lot of details, but we will see sufficient details. Then we can go into the TCP segment structure. So this is the packet, well, the way a TCP segment looks like. We can see that there is a header, which is a variable size header. So there may be options in TCP that can be used for different purposes. For example, to compute or to negotiate the the maximum segment size. But the important thing is the fixed header of TCP. Here we represent that in a 32-bit, aligned to 32 bits, so 4 bytes. So we have the source port and destination port. We saw the concept of ports in previous lectures. And then, and this is basically the same thing, is to allow to multiplex multiple connections on even the same sender and receiver hosts. And then we have sequence number, which is the pointer of considering the whole byte stream of data that is being sent. What is the first byte that is contained in this segment, if the segment contains data? Because as we will see, there may be segments that control no data at all, only the header for control purposes. The acknowledgement number is basically the number that this sending, that the sender of this TCP segment is expecting to be received from the other end. Remember that is bidirectional connection, so that is where we are putting a number saying the next byte that I expect to receive is number whatever, meaning that the previous ones has been correctly received. Okay, and this is done. This is counting in bytes. Okay, we are not counting on segments. This is counting on bytes. So it's a byte number. It's an index of the byte that is being sent or the byte that is expected to be received next. Okay. Then there is a set of well, there is a header len, just to distinguish whether there are options or not. Some parts, some bits not used, and then there are some flags. Okay. I will not go into all the details. There are some that are important. For example, the acknowledgement one, that is, if it's set to 1, that means that whatever is in this field of the acknowledgement number is really an acknowledgement number that is valid. It's not something that is there because the packet doesn't contain a valid acknowledgement number. And this is because there are some segments that are used when we establish the connection that still don't contain a valid acknowledgement number. Then there is the urgent bit that is not generally very much used to indicate that there is some urgent data in this segment. There is the push data now. That is also something that is not very much used, but it's basically saying send the data to the application right now. Don't wait. Try to minimize the time. Try to send that to the receiving side. And then there are some bits that are important, very important, because they are used in the connection establishment of TCP. TCP is connection oriented, so we need to set up a connection. These are the reset, the SYN, and the FIN. We will see how those bits are used when we see the connection establishment or connection management part of TCP. Then we have the receive window, which is a field that contains the number of bytes that the receiver is willing to accept. So it's kind of the size of the buffer, of the available buffer that the receiver has. And that is used, as we will see in the flow control part of TCP, by the sender to control, to adjust the number of bytes that are sent to the receiver without being acknowledged. To avoid to overwhelm the receiver by sending too many bytes. This is a field that is, since the urgent data is not really used very often, not very important, it's basically the pointer of the data contained in the segment that is urgently, that is the urgent data, because may not be all of the data contained may be urgent. There is a checksum, and this is like in UDP, it's an internet checksum. then options, and then the data, that the variable length data that we saw before. How are those sequence numbers and acknowledgement numbers used? Let's see an example. So the sequence number is the number in the byte stream of the first byte in the segment that is being sent. So let's consider this example between a host A and a host B that are running Telnet. Telnet is an application for a remote console connection. So if you remember when you are in the lab and you open a console, you can do ping, you can do trace route, you can do all these things. You can use Telnet to connect to another host and obtain this command line interface and be able to execute the same commands on the other hosts. Okay? So if we do Telnet, which runs over TCP over IP, once we have established this, for example, if in the host A we type C in the keyboard, we will be sending this, well, something representing that C in the data of the TCP connection of the Telnet. And for example, that may have a sequence number 42, an acknowledgement number 79, that meaning that host A on the other direction is expecting byte number 79 and the following ones. And the sequence number means that over the byte stream that is being sent from A to B, 42 is the number of the data that is contained. Okay, we have assumed that everything is already established a connection because we haven't seen yet how this is done. So this C is received by B. Since it's a Telnet application, typically what we need to do or we need to have is an echo from the host B to host A. So when we are typing in a console with Telnet, we can have some meaning of assurance that the data has been received by the other end. And that is achieved by receiving back the same character that we have typed. And that also provides some level of some idea of the latency involved, because if we type C and we don't see C printed in our screen, because it takes time for the other end to echo, that may mean that there is a long latency, or maybe that that has not been received actually yet to the other end. So that's why we do this echo. So the host B echoes back that character C. You can see that the sequence number is the 79 that was included in the acknowledgement number. So it's the next one that we expect because there was nothing else being sent from B to A. And B is acknowledging that it received the previous byte that was 42 and is expecting 43. Here we are assuming that the data is only consuming 1 byte of data. Okay, so that's why we go for 42 to 43. When we receive this in host A, basically that is printed in the screen of host A because of the Telnet. And assuming that we are not sending anything else, from the TCP side, host A has to acknowledge to host B that that C that was echoes back has been received. And that's why we send a sequence 43, although there is no data, and acknowledging that this C has been received, saying that the next one that we expect is 80. Okay, so we can see that here the sequence number is the acknowledgement number includes the sequence number of the next byte expected from the other side, and it's a cumulative acknowledgement. If I say that I'm expecting 80, that means that I have received everything that has been sent before. And as we will see later, we can acknowledge more than 1 byte or even more than 1 segment, because when we say acknowledgement number 1000, that means that we have received up to 999 or up to the byte label with 999 before. So how we can receive out of over segments? Well, most of the implementations are capable of receiving out of over segments. How to do this is up to the implementation. So the spec doesn't say how to do it or whether actually is that if that is needed to be done or not. Simpler TCP implementations could not accept out of order and require to retransmit everything in order again to be able to be processed. It's not something that regular current TCP implementations do because they are complex enough and very powerful. But the implementation again, or the specification, sorry, doesn't say how to do that. Then, how we ensure this TCP reliable service? So TCP creates this reliable data transfer on top of IP, which is unreliable. Remember, IP is best effort, and we don't have any guarantee that the data is being actually received, that is received in order, and there is not applications or whatever. So we do this by pipelining segments and by using cumulative acknowledgements. And as we will see later, TCP uses a single retransmission timer, only one, even though it may be sending multiple or may have multiple TCP segments that has been sent pending to be acknowledged, but we only use one retransmission timer. And this is for to simplify the state and the way this is done, because keep in mind that on any given device, we may be having even thousands of TCP connections at the same time. So imagine if we had to have multiple TCP retransmission timers for each of the connections. When do we have retransmission? So in order to provide this reliable data transfer, if a segment is lost because the IP layer loses that for whatever reason, because again IP is unreliable, TCP will be the one to retransmit, to send again that segment that has been lost. How this is done, or how this is triggered? This is triggered by two different things. Timeout events, so we have this retransmission timer, and at some point in time we send a byte and we didn't get an acknowledgement of that being received. We wait until some time. If this is not received, that triggers a timeout, and that's used to retransmit that segment at least, and maybe the ones after that as well, but at least that one. And another way of detecting that something has happened is duplicate acknowledgements, because if we are sending a byte stream of data and only one is lost, but the one after that has been properly sent and received, we will see as next that the TCP receiver side, we will start sending acknowledgements saying, I've received a segment, but I'm still waiting for this byte, the one that the first byte of the segment that was lost. I continue receiving segments that contain data that goes after that, but I'm still waiting for that piece to be received because I have a gap in my byte stream. That will generate duplicate acknowledgements, because all those acknowledgements will be saying, I'm expecting this byte to be received. And that can also be used as a trigger for the sender to say, I think that particular segment at least has been lost. Okay? So we are going to initially consider different variations of senders and receivers to explain some concepts, and then we will start putting or adding complexity. So we are going to consider initially a simplified TCP sender that ignore duplicate acknowledgements and where we don't have flow control or congestion control. Okay. Then, having that in mind, if we have we can see what are the sender events that are basically considered or that may happen. So the first one on the sender side, again, we are on the sender side. Remember, consider that we receive data from the application. So application is sending data on the buffer, is writing data on the buffer at the sender side. So the TCP stack will create a segment with a sequence number, the one that goes next of the last bytes that has been sent. Remember, this segment number is the byte stream number of the first data byte in the segment that is being sent. And it will start a timer if there is not one already running, meaning that there is already something pending to be acknowledged. But let's assume that everything has been acknowledged before. So we start a timer and we set that timer to some value. Okay? And we send, or we provide basically that segment with the header of TCP and the data to the IP layer, and the IP layer, and of course we will be saying to the IP layer, send this to this destination IP address. Because remember that a transport address is composed by the IP address and the port number. Okay? The port number is containing the TCP header, the IP address is containing the IP header. So we are sending the segment to IP layer saying send that to this destination IP address. Then, if there is a timeout, that's another event. That means that the retransmission timer that we established got to the timeout value, and then what we have to do is retransmit the segment that originated that timeout and restart the timer. Okay? And another event that may happen on the sender is that we actually receive an acknowledgement. If we receive an acknowledgement of something that is still pending to be acknowledged, we will update what has been acknowledged, so we know that those bytes has been received already. We can forget about those. And we will start a new timer or reset the timer if there are still pending outstanding segments to be acknowledged. If there are no more, we just stop the timer and we keep on waiting for new data received from the application. So this is basically the way that looks like in an algorithm way. I will not gonna go into the details. You can take a look, and it's important that when you take a look, you see these variables that we typically use, send-based, which is basically send-based -1 is the last cumulative acknowledged byte. And what you can see in the example, this is where I'm not gonna spend a lot of time. Please go check that you understand this, check the examples from the course, check the exercises that we have, and if you have questions, we can go and try to address those in a class or in a session with me here or remotely. Okay. So some retransmission scenarios that we may consider. Those are examples. Okay, simple examples. So we have in all of them host A, host B, sender and receiver, client and server, whatever you call them. Typically, we are focusing on data only going from A to B, but it's not the only possible case. So imagine that we have host A sending 8 bytes of data with sequence number 92, and that the acknowledgement, so the data is actually received by host B, but the acknowledgement is lost. At the time that the host A sent that segment, started a timer. We are considering nothing else is previously pending to be received. And since the timer expires here and we didn't receive the acknowledgement, we retransmit and we establish another data. And when we receive the acknowledgement, we update our internal variable or internal state saying, okay, the other guy has received up to 99. Okay? So it's expecting the segment byte or the byte 100. You can see sequence number 92 and 8 the bytes of data. That means 92, 93, 94, 95, 96, 97, 98, and 99. Those are the bytes included. So the next one that is expected by the receiver will be 100. Okay? This is the lost acknowledgement scenario. We may have a scenario where we have what is called a premature timeout. For example, here we are sending two segments of 8 bytes and 20 bytes. We have a timeout timer here for the sequence number 92. We have the acknowledgements, but the acknowledgements are received after the timeout is triggered. So at the point that the timeout expires, the host A will resend the 92 segment, okay, or the segment that contains the byte 92 and the following 8 bytes. And when we receive here the data, since the guy has received not only that segment that was already received by the one after that as well, the acknowledgement that is being sent from B to A is not ACK equal to 100, it's ACK equal to 120 because this is what is expected. Up to that has been received, up to the byte 119. And once this is received here, the receiver will update the send base to 120 and we will reset, remove the timers. Some more cumulative acknowledgement scenario. Well, this is something similar to the previous one. If we have host A and host B, we send the first segment, the acknowledgement is lost, but we have another segment being sent, and that acknowledgement is not lost, and the timeout is long enough. That will mean that by the time this acknowledgement is received, since it's cumulatively acknowledging not only these 20 bytes, but also the 8 bytes received before, the sender doesn't need to retransmit anything because actually everything was received, only the first acknowledgement was lost, but by the second one being cumulative, that's good enough. So how acknowledgements are generated. So this is a bit special from TCP, and there are variations. Again, this is one of the things where we may have variations of different TCP implementations. So when you see here events at the receiver and what we do at the receiver, up to or triggered by that event. So imagine that we receive an in-order segment with the expected sequence number. All data up to that one has been already acknowledged, so that's perfectly fine. Typically, what implementations do in this case is not to send an acknowledgement right now, but to wait up to 500 milliseconds. Again, the time can be different among different implementations for the next segment. So we are delaying the acknowledgement, basically saying or thinking the rationale is, let's try to acknowledge multiple segments with one. So in this case, we minimize the number of segments, control segments that we send on the other direction. This is considering that the receiver doesn't have any data to send to the sender, because remember that is duplex, the connection. If that's the case, we may be sending data on the other direction, and while we send data, we acknowledge at the same time, because the acknowledgement number and the sequence number are always present in a TCP header. Okay, but assuming that there is only data from the sender to the receiver in this case will wait. Then, if we get a new in-order segment with expected sequence number, and we have one segment pending of being acknowledged, in this case, we really do send the acknowledge, the ACK, acknowledging both the previous one that is pending, that was delayed, kind of, and the new one. Okay, and in this case, instead of sending two acknowledgements, we are sending just one. Then, what happens if we receive an out-of-order segment higher than the expected sequence number? That means that we have a gap. We have not received something that was in between. In this case, we immediately send a duplicate acknowledgement indicating the segment of the next expected byte. It's a duplicate acknowledgement because in general, with some exception, but in general, we have already acknowledged what we are expecting. And since we are receiving a new one with a gap, and we cannot acknowledge what is in between because it has not been received, I'm acknowledging again what I was expecting before. And this is called duplicate acknowledgement. And that, as we will see later, receiving duplicate acknowledgements may be used as an indication that something has been lost without waiting for the timeouts that sometimes are too large and will make the TCP implementation wait too much to detect something that we can detect, a loss that can be detected with a duplicate acknowledgement. And another thing that may happen is arrival of segment that partially or completely fills a gap. So if that's the case, so we can move basically our pointing of what is expected to be received, we can immediately send an acknowledgement saying, okay, up to that, we have already received. So basically we are covering part, if not all of the gap that we had before. So that's a way we use this cumulative acknowledgement and the way we generate acknowledgements to be as efficient as possible. Then, a mechanism of TCP that is important to understand is fast retransmit. So the timeout periods often are very long, and that implies that we have to wait a lot before resending a lost packet. So one way of detecting a packet loss without relying on the timeout period only is to detect loss or to infer that has been a packet loss via duplicate acknowledgements. So if the sender is sending a lot of traffic, which is typically the case in many scenarios, for example, if we are sending a file, or even if we are sending just pieces of a web or something like that, then if a segment is lost in this dialog, but the following ones are received, basically the receiver will say, okay, I'm still waiting for this gap or this byte or this segment that is in the gap that we have. And as we saw before, in this case, we are sending acknowledgements for the byte that we are still expecting, although we are receiving new packets. And that will generate duplicate acknowledgements. So if we receive 3 duplicate acknowledgements, that can be used as an indication that something has been lost, and we resend before the timer expires. So that's what is called fast retransmit. And this is an important feature for the kind of retransmission on the sender side. Okay, this is represented here in this figure. We send a data byte, segment, with some bytes. And then we send another one, then another one, then another one. So we're in the process of sending a lot of segments, because the window we will see the flow control and the connection control allows the sender to send all those segments, all those bytes at the end, because segment is a number of bytes that are sent. When we receive the first, host B send an acknowledgement, but the second one not, because the segment was lost. But when we receive the third one, we send an acknowledgement that will contain the same number than the first one. When we receive this one again, including the same number that is one, and the same thing here. And the third duplicate acknowledgement, because this, and this will have basically as acknowledgement number the number of the sequence of this segment that has been lost, because this is what is still being expected by B, although new data has been received. Then at this point, host A, without waiting for the timeout timer to expire, will resend that segment to host B. Okay, and in this case, host B will be able to cumulatively acknowledge everything. That's the way it works. And that's the first retransmit algorithm. I will not go into the detail. Again, you can take a look and see if you understand everything from this. And actually, that's it from my side. I try to keep it short, as I mentioned at the beginning. So I hope this is useful for you guys. And if you have questions, just let me know, either me or any of the other lecturers involved in your group, and we will be happy to address those. Thank you, guys, and have a nice weekend or have a nice day whenever you see this video. Bye-bye.